Okay, so welcome back, everybody. Thanks so much for being here and for your attention. I'm actually really excited about this particular session. I'm a bit of a methods person. I'm not a great methods person, but I think that there's something that's very fundamental and very important about having consistency about the things that we do. So we have common terminologies, or at least a common understanding about the way in which we derive variables that we do in many of the different studies. Across a series of presentations we've seen so far, we've seen a variety of different methods used, and it'd be great to have some kind of discussion, not only on the analysis part of it, but perhaps also on the methodological components. So I've got a few talking points and questions that I'll bring up specifically, but also it would really be great to have a good discussion amongst all of us. You know, maybe as ambitious to come up with some consensus, at least on certain variables, not entirely necessary or expected, but at least even some things that are not the best types of approaches. At least if we can sort of eliminate things that are not the best approaches, that might be even a really solid achievement. So with all of those goals in mind, as I said, we've allotted a lot of time for discussion, and so I won't take any more time away from our first presenter, Antonia from UCL.
Thank you very much for inviting me to be here. That's a really great introduction, and I'm always feeling a bit nervous about this being put in the methods section, because I'm going to talk about a whole bunch of methods that are nothing to do with anything we've heard about so far. So it's going to be a completely different set of questions to what people have been talking about so far, and a completely different way of looking at stuff. It's not completely different. I mean, there are overlaps and things, but some of this work that we're doing at the moment in my lab and the stuff I'm excited about, and the stuff I really want to talk to you about, is pretty different to some of the other things we've heard. So I thought I'd just throw out there a few ideas about what I've got and how we can look at social interaction using methods that are kind of coming from action cognition, but then also where we can go next with this kind of work. So this is a picture I grabbed last week of a social interaction. It's a fairly fleeting social interaction where my postdoc is presenting a poster at a conference. It's also a sort of, pretty unscripted and maybe complex social interaction. So Dimitri's over here has noticed I'm taking the photo, even though he's meant to be trying to ask a question to Alex, and she's listening pretty hard to try and work out what he's asking about the poster. So there's kind of even just, this very fleeting grabbing a photo. There's quite a lot of different things going on. And the kind of question I'm really interested in these days is, how do we capture these very ephemeral, real-world social interactions? How do we do science on this stuff? Not on, the controlled experiments that you do in the lab where you do 100 trials of the same thing over and over again. But can we really do science on this stuff? We put numbers on it. Can we have theories? Can we make sense of everyday behaviour and link that back to brain mechanisms and to cognitive processes? So that's my kind of overall question that I care about, and it turns out to be pretty tough to look at. But I'm going to give you, so today I'll talk a bit about some of the methods people are using at the moment. I'll talk a bit about the theories that I'm developing, and I'll talk a bit about some of the methods that we're just starting to use and I think are going to become very important in the future. But because I've been asked to focus on methods in this talk, I'm sort of going to start off imagining that you are a lab and maybe you get some new PhD student who comes along and says, I really want to study social interaction, the whole of my PhD. And I'm kind of, an enthusiastic new student and I don't know much about it, but what are the kind of principles that we might want to think about in terms of using methods and designing experiments to study human social interaction? So, our typical experiment, we've got a participant and a laptop, or maybe some kind of motion tracking thing, and so we can think about what kind of stimulus are we going to have, what kind of responses are we going to measure from the participant, what kind of tasks are we going to have the participant do, all our traditional kind of cognitive questions. And I'll go pretty quickly through some of these before going on to some examples of stuff that we're actually doing. In terms of the stimulus, one of the main considerations for thinking about social interaction is what level of ecological validity are we going to go. Traditionally we've done lots of stuff with still images. We can start to move into video. We've done some work using virtual characters, and now increasingly in my lab we're using real people. 2 real people coming into the lab, because at this end we've got much more ecological validity. I think there's a bunch of interesting effects that you get here that you don't get in any of the other things. We've also obviously got much lower experimental control when we're dealing with real people compared to dealing with still images and getting reaction time data. So once we're getting down into this domain, we've got to be thinking about different kinds of methods and different ways of thinking about it. But we've got a review paper, at least on how we can use functional characters for research and what are the advantages and disadvantages of that. But that's kind of one dimension of consideration. Another dimension that's worth thinking about is the data we're recording, and there's a lot of people here with a background in action and motor controls, so we've got to be some familiarity with motion capture, which I'm often having to explain from scratch. The brilliant thing about motion capture is it gives us some very rich data. We'll be getting traces on each trial over time and movement. I'm often measuring the height of movement, whatever movement parameters you like. And the challenge with this very rich data is there's then millions and millions of different things that we can analyse from it. We can analyse the duration of the movement, the height of the movement, velocity, acceleration, all sorts of stuff, and it probably depends on the task, on the context, on what research question you asked, which of these we're going to measure. So the only advice I have here is that if we do experiments twice, we do it once, find our result, pre-register, and do the whole thing again, or do it again with an extra control condition or something like that. Because when you've got this many parameters, I'm not terribly optimistic that we're all going to say, one parameter is the most important. It depends on the task, it depends on the context, it depends on everything. But I do get a bit frustrated when I see papers where every single paper picks out a different parameter, and that choice of parameter looks fairly post hoc. So my feeling is that pre-registration is probably the way to reduce that problem at least, and reduce the sort of cherry picking of, I'm going to pick the parameter that gives the result I like. So the main thing that I'm going to be talking about, the sort of dominant theme of this talk, is really what kind of tasks are we using to measure and understand the social interaction components of action. And I'm kind of starting from the assumption that if we do an object-directed action on your own, you pick up a glass of water or something like that, you're pretty good at doing that, you're pretty efficient, maybe you're optimal or nearly optimal in some kind of optimal motor control kind of sense. And so then I'm using that solo action as a standard and thinking, how does that action change when I now put this in a social context? So it could change because the social context imposes a different task. It could change because maybe I'm getting either some priming or interference from something I'm seeing from the other person, or it could change because of other feelings to do with feeling being watched by the other person, by how you're interacting with the other person. So I'm going to talk through some experiments that have been done with each of these different kinds of tasks. And in particular, I'm thinking about, does this kind of experimental design, does this kind of task show us something that's uniquely social? Or is it just showing us a general property of how the perception action system works? So first of all, there's been quite a lot of studies looking at, for example, changes in the kinematic patterns of behaviour when you act with other people in different contexts. So maybe if you're told to cooperate with another person, or hand an object to them, or time your actions to match theirs, or if you're told to compete with another person, there's a variety of task instructions that you can impose, and as you'd expect, your kinematic parameters change roughly in the way you'd expect. If you're told to compete, you tend to go quickly because that's what the task imposes. So I think we can certainly learn interesting things here about how these different tasks work, but I don't yet know of studies that have shown that these effects are specific to a social interaction. If you were told you were competing with this orange robot, which had a different dynamics, would you also show exactly the same pattern of movement simply because you've been put in a competitive context? And so it's the task that's imposing the kinematic changes rather than the other person, the fact that it's social. I think we don't quite know the answer to that yet. A different kind of effect that's been pretty widely studied is things like interference effects. So the idea that seeing another person's action might change how you produce actions. So one of the first studies looking at this was from James Kellner, showing that if you're told to make repetitive horizontal movements and you see somebody else making vertical movements, then you've got a higher variance than if you're observing someone making horizontal movements. So what you see interferes with what you do. And then we did a study a couple of years later showing the effect the other way around. So if you're lifting a light box while you're told to judge the weight of the box that somebody else is lifting, then you're biased compared to if you're lifting a heavy box. So the action you're doing interferes with your judgment of the action you're seeing. So we can get these interference things going both ways round. It's a perceptual action kind of overlap. Similarly, this is just one example study of imitation, or probably in this case a kind of kinematic priming. So in this study, participants would see a virtual character who points to a series of dots, and they're told to point to the same dots of the demonstrator in the same order. What they're not told is that the demonstrator on some trials is making high movements, and on other trials is making very low movements in the table. People would typically make a low movement because that's the lazy thing to do, but if you've just seen a high movement, then the height of your trajectory above the table is higher compared to if you just see a low movement, and that effect is a bit smaller if you've got a diagnosis of autism spectrum condition. So this kind of thing is a sort of kinematic priming effect, a form of imitation. And I think that both of these factors, the interference studies and the priming, are kind of opposite halves of the same thing. I expect everyone in this room is on board with the idea that there are overlaps between perceptual processing and motor processing. So those could be called visual motor associations, or mirror neurons, or associative sequence learning, idiomotor theory, event coding, affordances. And I know there are very subtle and important differences between those terms, but for the moment I'm kind of lumping them all together and saying this is a general visual motor association system. And again, we can look at that in terms of brain systems, but the point that I want to make here is that all of these things apply to non-social stuff and just as well as to social stuff. The brain mechanisms here apply to social, seeing other people's actions, but also seeing objects, and all of these kind of mechanisms can apply just as well to non-social stuff. So there's a strong field of research on these kind of perception-action interference and perception-action priming mechanisms, but I don't think any of them are terribly specific to the social domain. I think they can apply to it. So the question then becomes, what can I, when I'm interested in social interaction, what can I look at that is maybe specific to the social domain? And here we're going to go way back in history to the first social psychology experiment ever published, which was Triplett in 1898, and he studied children performing a task where they had to reel in a fishing line as fast as possible. And he found that when the children were told to do this task in pairs, they did it faster than when they were alone. And he argued that this was some kind of an audience effect or an enhancement from working with another person. And that's been studied, studied in a lot of detail in the 60s and 70s, and since then it's been somewhat neglected. But I think the strongest theory that's come out of there is the idea from Bond that the audience effect really arises from thinking about self-presentation. It's about how do other people see you and judge your performance. It applies, of course, to a wide variety of different tasks. So motor tasks, cognitive tasks, empathy tasks, all sorts of different contexts. It can go up and down in different ways. And a more recent paper from Antonia and Wavelet kind of made a slightly stronger link between this idea of an audience effect and the process of reputation management. Thinking about your reputation and what do other people think about me, and the idea that that might be a mentalizing process, a theory of mind kind of process, whereby you can send signals to another person. If you ostentatiously give money to charity, you're doing that because you want to show off what a rich and lovely person you are, not necessarily just because you're altruistic and kind-hearted. And thinking about how those kind of processes might be used in a social interaction. So it's a complicated area, and there's a lot of different explanations for why people might change their behaviour in the presence of an audience. There can be low-level explanations in terms of changes in anxiety, but the rich, elaborate explanation is the kind of idea, you know, when you're in this kind of job interview situation and you're thinking, oh, what are these people thinking about me? I've spilt the ketchup on my shirt, they think I'm horrible, what should I do to change their impression? Maybe if I smile, then they're going to think I'm marvellous and give me the job. So these kind of processes might be part of what's in an audience effect, but it's not always this kind of evaluative positive, showing off, signalling kind of thing. Anyone who's had a 4 or 5-year-old knows that the thing that's important to that kid is not just that they can go down the slide, but that mum and dad have to watch me go down the slide. You know, kids are very keen on being watched and wanting to show off what they're doing. And I think in terms of cognitive processes, all of these things have been talked about in a variety of ways in terms of self-related processing, reputation, mentalizing, communication. It's proved really tricky to pull these things apart. It may well be that there isn't a way to pull them apart, that they all overlap. But those are the kind of ideas we've got for cognitive processes that might be involved in an audience effect, in changing your behaviour according to whether or not you've been being watched. So let's again think about how this concept of an audience effect might apply to the question of basic motor actions. And again, we've got this idea that your action performed alone is something fairly accurate, something fairly efficient. But when there's an audience watching you, you're now potentially doing that action for different reasons. You could do that action just because you want to do it for yourself, but you could also do it to communicate something, to allow the other person to learn something, to establish some kind of social connection with the other person. It could potentially be a bunch of extra motivations coming in when someone else is watching you. And we've been thinking about this in terms of a model of imitation. The question of why is it that people are such prolific imitators? We imitate stuff all the time, and we're often imitating stuff that isn't about learning new skills. So I'm going to use this example picture of these two kids quite a lot, and I'm going to assume that the big sister pointed to their nose first, and then little sister copied and pointed to her nose. And these kids don't need to learn anything. They know where their nose is. They're not acquiring any new motor skill by engaging in this kind of imitation. And what I'm suggesting is that rather, what people are so often doing in imitation is signalling a social connection with the other person. So it's a kind of non-verbal, implicit conversation that goes something like, oh, look, here's a funny thing to do. I can touch my nose. Little sister says, I can do that too. I'm like you. And big sister sees that. And yes, we've established a social connection. Now we'll move on to play the next game and touch our ears or wave our hands in the air or whatever it is. So that was my kind of hypothesis about what imitation might be doing in social interactions. But if we want to actually test that, then what the simplest way to test that is essentially to blindfold the big sister. Because if we blindfold the person who's sending the imitation signal, then we still send exactly the same signal, but we know she isn't going to get the reply. We've taken out the potential to realise, has my little sister copied me or not? And so once that's been taken out, we predict that the little sister is not going to bother to copy because the message can't be received. If this is being sent as a message, then there's only a point, you only need to send that message when the other person can get the message. So our prediction is that people are going to imitate more when they know that another person can see their action. And we've done a few experiments that test that with things like video, which is kind of nice, but video, you're not really seeing stuff. So what we wanted to use as a proper test of this was something where we've got two people interacting together, and we set it up in an augmented reality environment. So we have two participants standing side by side. They've both got polyhemous markers on their right index finger, and they can use the polyhemous markers to move blocks about in the virtual space. So their task is to move blocks from one table to another in the virtual space, and we can motion tap them as they do that. And each trial has a set structure with 3 phases. So the two people have been assigned roles. One's the leader, one's the follower. And first phase is the demonstration. So the follower is told, close your eyes. The leader watches the computer demonstrate how to move blocks. And the participants are told at the beginning, your job is to move these blocks in the same order as the other person. So it's a bit ambiguous what order to move them in, and they're told, concentrate on the order, try really hard to remember the order and get it right. What the follower is not told is that the computer is also demonstrating 3 different trajectories. So sometimes the computer has a low trajectory, sometimes medium, and sometimes high. And the leader has been told to carefully follow that trajectory, but the follower has no idea that trajectory is relevant for them. So the leader sees the demonstration, which has both the order information and the trajectory information. Then everyone opens their eyes and the leader demonstrates the actions. At this point, what we're calling the height of the leader's movements. So we know, has the leader done a good job of copying the computer? What exactly is the leader demonstrating? And now comes the test part of the trial when the follower has to do the same actions. And again, we can measure the height of the follower's actions. The key manipulation here is what's going on with the leader. The leader could have her eyes open or closed. And the states of people's eyes as open or closed is always controlled by a voice command that's coming out of the computer that everybody can hear, so the little speaker saying, leader open eyes, leader close eyes, follower open eyes, follower close eyes, at all of the different points through the experiment. So everyone always knows what the status is in terms of eyes open and closed. And the two participants are standing right next to each other. So you're not directly seeing the other person staring at you. You can kind of get a bit of your peripheral vision, but your primary source of knowledge is this voice command that says, leader, close your eyes. And so our prediction is that, first of all, it should be imitation. So the height of the follower's movement should correlate the height of the leader's movements. And secondly, that correlation should be stronger when the leader's eyes are open, like the potential of social signaling. We did this study, first of all, in 22 dyads and developed our analysis protocol and decided on exactly what our parameters were going to be. And then we did a pre-registered replication with another 30 dyads. The results look like this. So the follower very consistently correlates with the leader. And in both study 1 and study 2, that effect is stronger when the leader can see, when the leader's eyes are open. So it matches our prediction that imitation in a live dyadic interaction in naive pairs of adults really can be being used as a communication signal. It's not just that you're being primed by the thing you see or you're copying, but because of some low-level priming mechanism, it really is being modulated by this top-down knowledge of whether the other person can receive your social signal or not. So that's our first sort of test of a hypothesis-driven bit of a social interaction. But let me see. So my overview, I've kind of got down to here, imitation signaling. And in the last 10 minutes or so, if I have another 10 minutes, yes?
Is it both people's eyes open? Does it work no matter whose eyes are closed or only one?
So they had fixed roles, and in this bit, phase 3, it was only ever the leader who had their eyes open or closed.
Okay.
Yeah. So the the beginning of the study, they were assigned the fixed roles of leader and follower, and then they stay in those roles for the whole thing. Okay, so that's one way in which we can, I guess, draw on some of the ideas from the audience effect and ideas about signal and communication to kind of try and test hypotheses about what's going on in social interactions with a moderately realistic task. At least we've got, two people interacting with each other rather than just one person sitting in front of a video. But the last thing I want to tell you about is some studies that we're doing that are trying to get even closer to the real world. Again, I've been studying imitation in my lab for 12, 15 years, something like that, and we're often doing these very, very simple tasks. And then we'll write papers where we're saying, oh, lots of imitation happens in real world social interactions. And there's some papers coming out of social psychology saying, imitation in conversation is really important as a social glue and bond people together and things. We thought, but what does this imitation in everyday behaviour actually look like? There's a lot of papers saying it's there, and very few that actually characterise what do we know about the mechanism of this? What do we know about the timing? How fast is this? How does it work? And so we thought, well, let's actually just go to real interactions, get pairs of participants, tell them to have a conversation, record the data. So again, they've got polyhedral markers on their foreheads and track what's going on here. And we thought, well, let's have possible models that could give us some idea of what kind of coordination might there be between these two people's head movements in the social interaction. So maybe they're in sync with each other. They're both moving perfectly in time together. And if that's the case, we can then say cognitively there must be some prediction mechanism because with the visual motor delay, you can't be perfectly in sync with somebody unless you're predicting what that person's action is going to be. So that's one possibility. Another possibility is that we're going to find a short lag between two people. So one person moves 200 milliseconds later, the other person moves. That could be just a basic reactive kind of mechanism. You don't have to be very clever to do it. It can just be see an action, and as soon as your motor system is ready, you do the action. On the other hand, if we're finding patterns of imitation with much longer time lags, and some of the studies from social psychology are reporting time lags of 5 seconds, 8 seconds, 10 seconds between the behaviour of one person and the mimicry behaviour from the other. Well, that you think must involve some kind of short-term memory mechanism. You don't typically do a discrete action and then, or see a discrete action and remember. You have to remember that in order to produce the same thing 8 seconds later. So if we find really long lags, then we'll have to start thinking about evoking mimicry. The last thing we might find is there's no pattern of lags at all, but maybe there's some interesting pattern going on in the phase relationships between the two people. Two people are sort of moving rhythmically with a phase. We might then want to turn to experts in dynamic systems theory to tell us what on earth is going on in phase relationships. So those were our 4 possible models, and we collected data from pairs of participants who were doing a picture description task. So this is a very simple way just to get people to talk. Essentially, one person, in this case the red person, has a picture, a complex scene from sort of National Geographic with lots of people in it, and then to talk about this picture in monologue for 30 seconds. After the 30 seconds of monologue, the bell goes ding, and then there's a further minute when these two people are allowed to have a dialogue about the picture. So we can separate out, is there anything different between monologue and dialogue, and throughout the whole thing, we're recording the head orientation of the behaviours of both participants. Each pair do 16 trials, and they swap roles each time. So one person is the leader, who's the person who's got the picture, the follower is the person who's listening, and then gets to ask questions later. And again, we did 20 dyads for our pilot study. We developed all of our analysis methods. This is a data set where there's very little established in terms of how to analyse it. We found some really interesting and quirky things that we weren't expecting. So we went and did another 30 dyads and pre-registered everything to confirm what's there. So, to analyse this data, our raw data that we get in on each trial is, does that work? I'll just wave my arm for that. So up there at the top, we've got a head motion trace from the red participant, and up there we've got a head motion trace from the blue participant. So that's the kind of raw signals we're getting on each trial. And to make sense of how these two relate to each other, we're using a wavelet analysis. So wavelet analysis splits this signal down so that we've now got time on this axis and frequency on this axis. We can see how much energy there is in little mortlet wavelets in each time bin and at each frequency. We can do the same for the other person, split their signal down to wavelets, and then cross-wavelet coherence looks at what are the time bins and periodicities for getting the same pattern of power across both of them. So it's looking at the correlation between the two. It's telling you, are there specific time points where these two people are moving at the same frequency, and in those time bins we'll say they're coherent. And then, because we've got so many trials and participants, we collapse this down over the time of the trial, and so we get a trace for each trial that just tells us the coherence at each of the different frequencies that we're looking at. We can take those traces and average them together over trials and average them together over participants to get an overview of what are the patterns of coherence looking like. Now that gives you a nice little wiggly line, but a wiggly line on its own isn't much use unless you can compare it to something else to say which bits of this are meaningful. And so to get the comparison, what we do is we get pseudo data by randomizing the trials we've got. So if a participant originally did this set of trials, trial 1, 2, 3, 4, we then take the data from the blue participant and shuffle it about, keeping the same ones with the red participant. And we're always matching trials. So we've got the same person, speaker or listener. We're doing this modelling up the trials within each pair of participants. So we've got the strictest possible control for all of the extra factors that are going on. The only difference between this trial with pseudo data and this trial with real data is that the real data has a genuinely live interaction and the pseudo data doesn't. Everything else is matched the same. And there's a couple of nice tutorials out there from Isartel on how to do wavelet coherence analysis. There's a lovely MATLAB toolbox that generates some pretty pictures which was developed originally for glaciology and understanding ocean currents and the temperature changes across the oceans, but turns out to be really, really good at generating pretty pictures for human actions. So again, I recommend downloading that if you're interested in doing this stuff. So that's what we do in terms of analysing this data, and the results we find look like this. So my plot at the top, these are the different frequencies of movement, and up at the side is the coherence level, where the red line is the real interactions and the blue line is the pseudo interactions. Then the plot at the bottom here is to show what's statistically significant. So it's exactly the same frequencies, everything matches up if you read downwards. And so this is simply showing the effect size for doing a t-test between the red and the blue line at each data point with a red dot when everything is FDR corrected. And so when we look at these, we can see a couple of interesting patterns here. It's pretty clear cut that this plot divides into two. It's two different things going on here. So when we look at the low frequency half, which is about 0.2 hertz to 1 hertz, we've got a reliable signal where the red one, the real interaction, is greater than the blue. That's a pattern of coherence, of mimicry, of interpersonal coordination. It matches up roughly with previous reports of what might be going on. That's cool, that makes sense. Then we look at the high frequencies. Just rely about anti-coordination. We had no idea where this was coming from. This is why we went and replicated the whole darn thing and spent another year on it to see, is this real or is this something that's gone wrong with our algorithms? But it really is there. So I'll talk you through now what both of these different components of the interaction signal mean and what we think we can understand from them. So first of all, we're looking at a bit more detail at the low frequency coherence. And the question we're interested in here is what's the time lag between the actions of one person and the actions of another. So we get out the Wavelet coherence plot for each trial, which is at the top, but as well as that, you can also get a plot of the phase relationships that go with each wavelet, so you can find out if the people are in phase or out of phase, and we use the coherence plot to threshold everything that's owned, so we're only looking at phase when you've got a coherence that's greater than 0.3, so you've got to have some level of coherence. And then we can take phases and put them into a histogram. So we end up with a phase frequency histogram. So these are all of our possible phases, and these are our frequencies. And the coloured blobs tell you there's a lot of data at this frequency falling at this phase. And then we add all of those up, again, over trials and over participants, and over the real data and the pseudo data, and end up with a plot that looks like this. So in here, the top half, the dark blue blobs, is that high frequency negative effect, which I've talked about before, but we'll come back to later. The bottom bits, these yellow blobs, this is the phase relationship that we've got in this low frequency mimicry behaviour. And so the kind of questions we can ask here is this just a constant phase that, you know, people are always, the leader is always, you know, 45 degrees, 30 degrees follower, or is it maybe that there's a kind of pattern that you can just about imagine this going on that way, and that would reflect a constant lag between the two. And, you know, looking at it, it looks to me like constant lag, but we thought we better build a little bit of a model. To do that, we built a couple of little teeny tiny toy models. So a constant phase model has two free parameters, the mean phase and standard deviation phase. Again, a constant lag model has two free parameters, mean lag, standard deviation of lag, and you run it through a few hundred times to get a pattern that's going to look realistically like the trials we've got. So we can generate those two models and find how each of those models best fits to the original data up there, and end up with the root mean squared errors. The root mean squared errors for the constant lag model are just a little bit smaller than the constant phase model. These are the optimal fits for both. So we conclude that the best fit to our data is a constant lag model. That constant lag model has a lag of about 600 milliseconds, which turns out to be pretty nice, because if you do a basic old-fashioned cross-correlation analysis, you also end up with a time delay of about 600 milliseconds. So doing a fancy, ridiculously complicated model ended up giving us the same results as a simple model, but it's a nice validation that we can get the same thing different ways around. And this lag of 600 milliseconds, that fits with our original cognitive model of a basic reactive mechanism. One person does a movement, 600 milliseconds later, another person does a movement. You don't need any fancy prediction there, you don't need any fancy memory mechanisms, it can just happen without anything else. And that's, you know, it seems simple, but I think it's really nice to suggest that you don't need stuff that's more complicated than that. So we can explain our low frequency data. What about our high frequency data? This high frequency anti-coherence, which replicated across 2 studies, which was completely unexpected. I'll start off with a couple of things that it's not. This does not, anti-coherence does not mean 2 people are moving out of phase with each other. That would be, they'd be coherent but with a different phase relationship. It's not a global change in the power of the signal. So it's not, if you just look over the whole trial and plot out signal power, there's no difference between the trials. It's not that one person is just completely static at that frequency. But when we looked back through a whole bunch of literature to say, what makes people move at these kind of frequencies, you know, about 2 or 3 hertz, what kind of thing might drive that? And that's a frequency of head movement when people engage in speech and conversation. But well, maybe this is just the speaker. You know, they're chatting away and they're moving their heads, they make their syllables. Maybe we're just picking up who's speaking and who's listening. So we wrote a little, this is really my postdoc, Jamie Ward, who's very good at this stuff. He wrote a little fast nod detector. We call these signals fast nods. And we said, let's just detect when within each trial is fast nodding happening and who's speaking at that point. So this is a couple of segments. Up at the top is a trace from the leader, and the little red dots in the middle there are the points. So these ones here are the points where the leader is showing fast nodding, and these are the points where the leader is speaking. And then this is the follower with some points where the follower is fast nodding, and the points where the follower is speaking. So our initial idea that this is to do with speaking, well it is, but it's the opposite way round, because it's the person who's not speaking, the person who's listening, who seems to be engaged in the fast nodding behaviour. And again, we can do this across everybody, and that comes out in the stats. So you can do the crude way where we classify on a trial-by-trial basis who's a follower and who's a leader, and we get a difference, or we can do it in a much more subtle time point by time point way, where we take each time bin and say who's listening and who's speaking, and again, the same effect comes out. Fast nodding is a behaviour of listeners. Seems to be only seen in the person who's listening in social interaction. So we think that, you know, this may be some kind of a social signal. It's something that happens in social interactions. We don't know what it is signaling yet. Is it signaling that you're attentive, that you're engaged, that you're caring about what the other person's doing? Could it be related to the speech rhythms of the person you're listening to? What other factors could cause this? At this point, when I give this kind of a talk, I would always get somebody sticking up their hand and say, but I can't nod my head voluntarily at 3 hertz. This is crazy. This signal can't exist. But actually, I think there's a lot of very meaningful social signals that you cannot produce voluntarily. It's pretty hard voluntarily to produce a genuine laugh or a Duchenne smile. These things are really meaningful social signals. So I think the fact that we can't voluntarily do teeny tiny nods at 3 hertz isn't really an argument against it being a social signal. It just means it's a pretty subtle one. And now that I know this and I sit in cafes and look out for it, you do see it. You know, it's subtle, but once you're tuned into it, you can pick it up all over the place. So we're devising studies to do things like create virtual characters who do or don't show the fast nodding behaviour and see how people respond to them, and really pull apart in detail what this kind of a social signal is and what might it be doing for our social interactions. So the summary for this part is that by recording data from real social interactions and looking at that in detail, we really can find out stuff about cognitive mechanisms, even though this wasn't the kind of experiment where you give people, you know, your traditional trial of do this and then do that. We just tell them to have a conversation. We can still find out things about cognitive mechanisms. We can find out things about real life interactions being more than just mimicry, that there may be new social signals in there, and then we can come up with new hypotheses for how to test these kind of things. And so I just want to finish off with a couple of hints of what we're doing in the future. Is we're basically going more and more multimodal, new data sets. We can track the whole body, the gaze, the face, the hands. We can track brain activation with ephemeral and get all of the data simultaneously from this stuff, so that hopefully we can then link that back to our cognitive theories and start to actually get theories of what's going on in these kind of dynamic social interactions and think of them as dynamic social interactions. At the moment, it's this idea about social signaling, what you signal at different points in the conversation, that's our kind of driving theoretical framework for where this kind of work is going. I do have a couple of videos of these new data sets and some other really cool stuff, but I'm almost certainly way over my time, and so I will stop at this point and I can show you the videos later if you want me to. Thank you very much.